of this afternoon session is Vladislav Kruglov. He's going to talk about moduli of surface and singular flows. So please, stage is yours.
Thank you so much. First, I want to thank all organizers for the opportunity to make a talk. My talk is on moduli of surface non-singular flows. The results were obtained in collaboration with Olga Pochinka and Galina Talanova. Here are Olga and Galina. And the subject of my talk is topological classification of dynamical systems. And first, I need to recall about two types of topological classification of flows. Classification in sense of topology in sense of equivalence and in sense of conjugacy. Two flows are called topologically equivalent if there exists a homomorphism of the Carrier manifolds and in trajectories of the first flow into trajectories of the second flow, preserving orientations of the trajectories. And two flows are called topologically conjugate if such homomorphism not only preserves orientations of the trajectories, but also the time of moving along the trajectories. And to find an invariant showing the class of topological equivalence or conjugacy is this means to find a topological classification for the class. The class considered in this talk is a subclass of the Morse-Smale flows. I want to remind what is a Morse-Smale flow. This is a flow which non-wandering set consists of a finite number of hyperbolic fixed points and a finite number of hyperbolic limit cycles. Besides, there is no trajectories connecting saddle points. So we have only hyperbolic limit cycles, which can be only stable or unstable, and three types of fixed points. Such class of flows was classified topologically for many times, but every time only in sense of topological equivalence. And next step is to classify these flows in sense of topological conjugacy. And the first question which can be asked in this area is the question of moduli of stability. The thing is each equivalence class can include infinite number of conjugacy classes. So Pallis found that for example, a flow with a separatrix connecting saddle points can enable, if a flow have a separatrix connecting saddle points, then in this equivalence class, this flow have a finite number of conjugacy classes, and these classes can be described by means of analytical parameter called modulus of stability. And of course, if to speak about limit cycle, then this gives at least one modulus of stability. I mean the period of a limit cycle. So now let me describe the class of flows considered in this book. Such class is an example of such class is described on the picture. The class of flows considered here is the class of non-singular flows with only two limit cycles on different boundary components of an annulus. There is no other limit cycles, and of course, no fixed points. Limit cycles are hyperbolic, and once again, no other limit cycles. The cycles are called C1 and C2. T1 and T2 are their periods, and K is the carrying annulus. We want to find whether such class of flows have finite or infinite number of moduli of stability. And to know that, we need to try to construct topological classification of such class in sense of topological conjugacy. The first step is linearization. By the system 1, we introduce on the plane the flow with the vertical trajectories as at the picture on the left and on the right. Then consider a homomorphism GI and the group of its action, and consider denote by phi I a space orbit of the action of such group. So we define as equivalent points such points as this one and this one, this one and this one. So we get a semi-cylinder P1 and P2 with a stable limit cycle on P1 and unstable limit cycle on P2. And Irwin in 1970s proved that there is a homomorphism between this flow on P1 and this flow in a neighborhood of C1, and between this flow and this flow in a neighborhood of C2. And the first result is that there is unique foliation, unique up to topological conjugacy near limit cycles. So if we consider a set of horizontal lines on the plane and then transverse it to cylinder and back to the annulus key, then images of these horizontal lines are these lines which are invariant up to topological conjugacy. And this means that there is infinite number of moduli because the function describing how image of the horizontal lines on the left and on the right, the function describes the relationship is the functional modulus of stability. This means that we have one functional modulus, and it means that we have infinite number of usual moduli of stability. And then it is useful to consider not a function on the plane, but on the circle, because this function have repeating parts of itself, and such function is a modulus, and there is the main result of the talk is the main theorem that two flows are topologically conjugated if all periods of the cycles are equal. pairs of cycles are both oriented either consistently or inconsistently, and function describing this relationships between two these images of horizontal lines on the plane are equivalent. So it's said, but I can't describe more precious. But so this is the main result, and this means that such flows have an infinite number of moduli, and it means that if we want to classify any class of flows with such domain restricted by two limit cycles, with a trajectory going from one limit cycle to another one, then such class would have an infinite number of moduli. Thank you for your attention.
Thank you, Vladislav.
For this presentation. Do you have any questions?
Yes, one question. Vladislav, these flows exist on the surface of the cylinder, or this exists in 3D space?
On the surface, of course.
Surface, yes.
It's like here on an annulus, on the surface of annulus, of course. There is a flow, and a neighborhood of a limit cycle is open from this side, and the trajectory goes, it infinitely goes this way. More close, each one, and on a cylinder is the same, almost the same, but this trajectory goes infinitely to the left, and the only difference is that it not became closer to itself.
Yes.
And so this trajectory have the same behavior as this, but here at the in infinite time it goes to this cycle, and here it only goes to infinitely far place.
Yes. And questions. In life, where exist flows for you?
In life, it's my favorite question. Always in life. So
maybe inner surface of the cylinder, inner surface of the cylinder.
Maybe
inside.
Now I can't remind any direct example, but of course this is part of classification of whole Morse-Smale flows, and Morse-Smale flows have such a situation as here, and to classify a Morse-Smale flow, it is necessary to consider such situation.
Yes, thank you.
Thank you.
Sorry, so just let me see if I understand it correctly. So you're not identifying C1 and C2, right? So you're not considering the torus.
I'm not. No, I'm not identifying. It is a flow not closed surface.
Mm-hmm.
It's closed but not compact.
Yeah. Maybe I have another question. So you are working, so in the very beginning, you was explaining you work with this notion of equivalence for manifolds, right?
Also for manifolds, but more for flows.
Yes, but I mean, so the flow is on a manifold.
Okay, yes.
Yeah.
Yes.
Do you have any extension to more complicated spaces, like, I don't know, simplexes, or maybe even just graphs? So if your flow is leaving on a more singular structure, maybe on a less smooth structure when you have actions or
no only
singularities.
But
Okay.
A surface can be any, but if to speak about graphs, there is one-dimensional dynamics, and such flows are different, but there are researches on flows on graphs and on, for example, on a circle, and it's very interesting and complicated, but it's not my case.
Okay. Okay, thank you.
Thank you.
If there are no further questions, then thank you as a speaker again.
Thank you, Chairman.